Hi, we are now closing Module 10, Renewable Energy Forecasting Advanced Topics, with its third block, Data-Driven Decisions. We have learned quite a lot of approaches, basic to advanced, to do modeling and forecasting for renewable power generation, but there still are a few things to fix. And maybe eventually, if we were to participate in a forecasting competition or try to improve models, we will have to make a lot of decisions on the way. This has to be data-driven, since what is to be done is to extract most of the information from the data and find the best way to model and forecast what's happening with this data. So what kind of decisions are we talking about? If you were to follow my proposals for modeling and forecasting, to use linear regression, polynomial regression, maybe online learning, there would be a set of meta-parameters that we have to decide upon. These meta-parameters could be, for example, the order of polynomial regression. If it's order 1, it's linear regression. If it's order higher than 1, that would be quadratic or cubic. If we go for local polynomial regression, we have to decide on fitting points and bandwidths for how broad we're going to look at the data around those fitting points. If we go for learning on sliding windows, we need to decide on the window size over which we're going to learn. If we go for online learning, we'll have to decide upon a forgetting factor or a learning rate. There might be some other meta-parameters depending on the modeling approach you want to follow and depending on your strategy, set of exploratory variables, etc. Also, you may want to compare totally different models, or you may want to consider the use of other explanatory variables you've not considered previously. And in all cases, you want that the use of a new model or of more explanatory variables would yield higher forecast quality. Here we think of forecast quality in a quadratic sense, so that means using the RMSE as a lead score to evaluate. So what could be a well-thought strategy to make those decisions? Remember, we are in a data-driven environment. Hopefully we have quite a lot of data, so the best we can do is actually to play with those available data. Here is an example with a data set with 1,000 data points. Let's say it's wind power generation data that's been collected, and we want to model what's happening with this data and eventually to get the best forecasting model we can get. We have 1,000 time step here, and power here is normalized, so it's between 0 and 1. So what could be a smart way to use that data set to make decisions about meta-parameters, modeling strategy, explanatory variables, etc.? What we're going to do, we're going to organize our own forecast competition where we're going to have our various potential alternatives to compete with each other. For that, we're going to split our data set in several parts, and typically you have to consider two parts. One that is for training, so if you make a choice of a model or a set of meta-parameters, you can train your model afterwards with least square, for instance. You could use some other approach. And then after you fitted your model on this training data, you use a part of the data set for validation. So there you use the data as if you were in operational conditions doing genuine forecasting. You don't try to tweak any more parameters, you don't try to learn, you are just testing your approach. We can generalize this idea with what we call k-fold cross-validation. And k-fold cross-validation in practice will mean that first you choose a reference score, we call it SC, and that can be, for instance, the RMSE, if we care about a quadratic loss. Then we'll divide the data set into k parts of approximately equal lengths. So in the previous slide, you saw just a split in two. We'll explain how we extend that to having k parts. And then eventually, for a given choice of a model and a set of meta-parameters, we can consider any possible combination of training set and cross-validation sets. So for all these possible combination, there is going to be a given set I, so one of this k subset of data, we're going to keep it for validation. Then we're going to train the model for a given model choice and set of meta-parameters. We train over the k minus 1 parts so that we have the training set. And then eventually we calculate the score, SC could be the RMSE, for the last subset of data. And we obtain this score value, SCI, for a given model M and set of meta-parameters theta. Since we split our data set into k blocks, and we can consider any kind of shuffling around of training data and cross-validation data, we do that. So we have k times results on a validation set, which will be different validation set. And eventually, we can calculate an average score, SC bar, for all these k validation data blocks. So SC bar is equal to the average of the score values for each and every block. K equal 10 is the most common choice, but nothing prevents you from considering splitting the data set in 5 subblocks or 20 subblocks or whatever you prefer. Let me illustrate that. For a data set with 1,000 time step here, we're going to split it in 10 equal parts, so that's tenfold cross-validation. And then we reserve one part, one data block, one subset of the data for this validation, over which we're going to calculate the score, so let's say the RMSE. And we'll use the other 9 blocks, subsets of data, for the training part. So when I is equal to 10, since I want to calculate the score I would obtain on this part, I train on this 9 first block of data, and I calculate my score for the 10th block of data. Then we're going to iterate, and we're going to say, I want to calculate my score for this 9 block of data. So I would learn for over the first 8 blocks and the last block of data, and it would calculate the score for this 9th block of data. If we continue with all possible combinations, you see eventually you would continue this way. You end up here for the 4th block. You learn over the first 3 blocks and the last 6 blocks of data, and you eventually calculate the score for genuine forecasting over the 4th block of data. Where you've done it for all these 10 blocks, you calculate the average of the scores that you obtain, all the SCI, and you obtain SC bar for your choice of model M and choice of set of meta-parameters tau. If you were to do this and obtain score values for your different models, for the different set of meta-parameters, then you can make a direct comparison and decide what is the model that yields the best cross-validation score, given a choice also of meta-parameters. Thank you for your attention, and now I would like to invite you to use the self-assessment quiz to check your understanding.